A steel bar A, B, C, D 4 meter long is subjected to forces as shown. Find the elongation of the bar and take the Young's modulus for the steel as 200 gigapascal. Now, so far you have only worked with one example with 2 different Young's modulus or 3 different Young's modulus. Now, most of the questions are based on one material. So it's easier, that means the E is common. Okay, if there are 2 materials, then you just split it as usual, but then each section you consider a different E. But if let's say it's only one E given, that means the material throughout is the same, homogeneous material. Okay, so in this question here, the first thing is you have to check the forces acting towards the total forces acting towards the left. Is it equal to the total forces acting towards the right or not? So towards the left, we have 10 plus 20, so that is 30. Then towards the right, we have 5 plus 25, so that is 30 also. So that means it is under static equilibrium. Okay, then you apply the principle of superposition, split it up into 3 sections as shown. Okay, as shown. Now, usually what I do is the principle of superposition for these diagrams here. Usually I draw it below the original diagram so that I can roughly got to see that which section, okay, that I am referring to. Now, for example, this is section B, so I can see section B throughout here. And then this is section C, so I can see C throughout here. Okay. So now, so split it up into 3 sections, 3 parts. Part 1, Part 2, and Part 3, A, B, B, C, and C, D. Okay, so we just picked up this 20 here. Straight away the 20. Okay, so this is 20. So for the equilibrium of this section, if this is 20, then this must be 20 here. Okay, the first part. Okay, everyone okay? Yeah. Then the second part here, okay, at section B, is only 5 kilonewton that is acting towards the right. And then at our section B here, acting towards the right is 20. So that means I must remove 15 from here. I must remove 15 from here to get the 5 here. So to remove 15 from here, so at the same section B here, I must consider the force acting towards the right instead of, the force acting towards the left instead of towards the right. So this is 15 kilonewton in this different direction. Is in the different direction as compared to the 20 kilonewton because we are removing forces. So we are removing 15 from 20 here to get back this 5 original force here. So since it is 15, okay, acting towards the left, then I must have a 15 acting towards the right for the equilibrium of this section. Then for the third part, for the equilibrium of this section, now you see at section C here, the original diagram is 10 kilonewton. So, but then that is acting towards the left. But then here I have 15 acting towards the right. So that means I must get a 10 towards the left. How am I going to get a 10 towards the left? So that means I must have a force acting towards the left. I must have a force acting towards the left, which is greater than this 15. Must be greater than this force 15 here, so that I get the force, a force which is acting towards the left, and which must be 10 kilonewton. So that is why I consider 25 acting towards the left. Okay, 25 acting towards the left. So this 25 minus 15, I got a net force of 10 kilonewton acting towards the left. So therefore, the third part here, that is section CD, now I have 25 kilonewton. So for the equilibrium of this section, I must consider a force in the opposite direction to this, and that is the same magnitude, so 25 kilonewton. So we have done with the principle of superposition, and we have found all the forces at each section. Then what we need to do is find out the area of each section, find out the area of each section first, okay, in millimeter square. Okay, up to you. You want to be want to convert it to meter square, or you want to remain it as in millimeter square, up to you. Okay, Then we find out the deformation every each section here, AB, BC, and CD. So we know that the deformation is given by the formula of force times length over area times Young's modulus. Force over area is equal, force over area is also equals to the stress sigma AB. But then since the question doesn't ask us to find the stress, so might as well I straight away take the forces using the FL over AE. If we have stresses, then we can take sigma L over E. Okay, so since there are forces, okay, and the question doesn't ask us to find the stress, so might as well we consider straight away FL over AE for the deformation. So AB, everything refers to section AB except the EE is the same throughout. Remember, only one Young's modulus is given. So you can find out XAB, the deformation of AB is this amount. Okay, so then you go for BC, the same thing. FBC is 15 kilonewton. Then the length, the total length is how much? Is 2 meters, so it's 2000 mm. So 314 is the area. Okay, sorry, BC. BC, the area is how much? Okay, BC, not CD. This area here should be BC, not CD. Why so many mistakes I did? Okay. So this is BC, okay? So the area BC is 314. So you've got the total, the deformation of section BC. Then the last part is CD. So everything CD, Young's modulus is common. So you can find out the deformation of section CD. And then you check each section here, each part here is tensile, tensile, tensile. So therefore, positive, positive, positive. When you find the total deformation, make sure it's positive or negative depending on whether it is tensile or compressive. But in this case, all tensile, so that's why it's plus, plus, plus. So the total deformation is 1.749 mm. Okay, so that's for this example. Thank you.